So to summarize, the annealed steels and normalized steels, okay, if you take these two, which one is cooled slowly? In annealed, you are cooling it slowly, relatively slowly, right? So that means relatively, since it is slow cooling, you have enough time for the grains to grow, you will be ending up with coarse perlite. Okay, in both the cases you will have perlite, right? And whereas in normalized steels, since you are going at relatively faster pace, so relatively you have fine perlite. Okay, so if somebody asks you what is the microstructural difference you see between annealed steels and normalized steels, you can see the microstructure of the annealed steel will have relatively coarse perlite. Now you tell me, I already told in the previous classes, which one will give you high hardness or better strength, coarse perlite or fine perlite? Okay, it is fine perlite. Okay, as I said, finer the grain, okay, or the finer the particle, it gives you a better strength property. Okay, it improves the strength, and why it is what will be discussed in the subsequent classes when we discuss about the strengthening mechanisms of the material. For time being, you assume finer the microstructure, better the strength properties and hardness, right? So yeah, if you see, relatively now you have red line, okay, that you get fine perlite when you normalize, and the blue line you get coarse perlite when you actually go relatively slow rate. Okay, you can compare these two with respect to the hardness. You see, as the carbon increases in the material from left hand to right hand side in the x-axis, as carbon varies from 0 to 1%, what is happening to the hardness? It is sharply increasing. You see, let it be fine perlite or coarse perlite. You see, with carbon changing from 0 to 1, it is giving the material so much hardness, right? See how small difference in the carbon can give you, say for example, assume a low carbon steel here, okay, and see the high carbon steel, the change in carbon percentage is very less, but still you are getting such a huge difference in the hardness here. You see, that means the hardness will drastically improve if you increase the amount of carbon in the alloy, okay, in the steel. Now assume in a given steel, okay, that means in a steel with a constant carbon, which steel will have more hardness, whether it is with coarse perlite or fine perlite? Okay, obviously you see here it is with fine perlite you have higher hardness compared to same material with, okay, coarse perlite. Okay, right. Similarly, you see the ductility. You have to remember one thing: you have strength or hardness and you have ductility. These two are always opposing properties. That means if you try to increase the strength, ductility tends to reduce. And similarly, if you want to increase the ductility, your strength or the hardness tends to reduce. Okay, these two are very difficult to have, these two combination. Okay, if you say I want high ductility as well as high strength, that is very difficult to achieve. Okay, so you see these diagrams. So accordingly, as the carbon percentage increases and your ductility is reducing. Okay, since you are increasing the hardness, your ductility reduces or the brittleness increases. Okay, right? So ductility is being affected because of increase in the carbon percentage. And again, within a composition with a particular alloy of some carbon percentage, you see the coarse perlite is relatively ductile compared to the fine perlite. Okay, so it is simple opposite to the hardness. Okay, hardness is high for fine perlite, whereas ductility is high for coarse perlite. Okay, of course you have spheroidite. Okay, that I will discuss after discussing about what is spheroiditization. Okay, that is a special heat treatment. What happens during that heat treatment, let us see. And even before that, we have to understand from this slide that the hardness of the material increases from fine perlite to, okay, decreases from fine perlite to coarse perlite, and again it decreases further from coarse perlite to spheroidite. Okay, I will tell you what is spheroidite in the subsequent slide. Okay, and right. So what does it mean? Okay, ideally if you want high hardness, you try to have fine perlite. Okay, and even without talking about the fine or coarse perlite, if you want high hardness, you always want to have high carbon percentage. Okay, the first step is to see if you want high hardness, try to have higher carbon percentage. And if you have the material already with some carbon percentage and you want to increase the hardness of that material, then you try to refine the perlite, okay, by going to normalization process. Okay, then you get the better strength, okay, and hardness, right? Now this figure again gives you the material with carbon percentage changing from left to right. So how much of yield strength that you may get. You see the normalized steel will be having more strength, okay, similar to the hardness compared to the unyielded steel. Okay, at any given alloy also you can see normalized having high strength, unyielded having relatively low strength. Okay, because you may have coarse perlite here and fine perlite here. Okay, right. So similarly, now similarly, if you see the yield strength, that is about tensile strength. Now this is yield strength. Okay, the same case, yield strength is also good for normalized steels, whereas for unyielded steels it is relatively low. Okay, so impact energy, okay, as the strength increases, okay, with the increase in carbon, you see strength or strength basically increases, whereas the impact energy reduces, or its ability to absorb the impact energy deteriorates as the carbon percentage increases, right? So similarly, percentage elongation also reduces with increase in carbon. This is general understanding what happens with increase in the carbon percentage within the alloy under different heat treated conditions, right? So next, as I said, another heat treatment process which is very important for the carbon steels is called spheroidizing. Okay, in spheroidizing, what we do, as you all know, in steels, okay, you have something called cementite. Okay, right, and this cementite typically, as you know, is nothing but carbide, right? So I have been telling you several times that this carbide is hard, highly hard material and brittle in nature, so very difficult to machine. Okay, especially this particular carbide. Okay, any carbides, okay, are there, since the hardness is high, difficult to machine them. So what we can do, if you can alter the shape of this cementite into some spherical shape, particles, okay, that is what we call spheroidizing. If you can have some heat treatment where all the cementite or the Fe3C or the this particular cementite can be changed its morphology into spheres, okay, then its machinability will drastically increase. Okay, its ductility gets improved a bit. Okay, so that is what we do in spheroidizing. Okay, so what is the heat treatment for that? A1 line. So typically you take this steel and heat it to just about 30 degrees below A1 line and keep it for several hours there. Okay, it's a prolonged heat treatment. It's not a small short period heat treatment. Typically, relatively, it takes very long time. All that you have to do is take that steel, keep it just below A1 line. What is A1 line? 723 degree Celsius, right? It is a right temperature. Now keep it for several hours and then cool it slowly to room temperature. That's all. So that is what spheroidizing heat treatment. So at the end, what you have, you see this, all these particles having round, okay, or spherical in nature, right? Because this morphology is being achieved because of this particular spheroidizing heat treatment. Okay, after this heat treatment, if you see the microstructure, you see the cementite in this particular morphology, which is now easy, makes it easy for you to machine the material. Okay, so if you see here, if we revisit this particular case, you see the hardness, okay, it increases with carbon, but the hardness is lowest for for the spheroidite material, because it has got this spherical cementite, okay, which will give its ductility. Okay, so you see the ductility of spheroidite in this particular case, which is highest, okay, of all. Similarly, hardness is, since they are all opposing properties, hardness is less compared to any other. However, it is desirable because it makes the steel more machinable. Okay, you can do spheroidization, machine it to the required size and shape, and then if you want to increase the strength, then do the heat treatment for the component, make the fine perlite and get the higher strength back again. See the beauty. Okay, that is what we can do in the, as engineers, we can schedule our heat treatments. Like, okay, you have carbon steel, you want to machine it, so first make it more machinable by doing spheroidization, then bring it to the shape and size. After machining is over, then do again heat treatment, either for example do normalization and get it back, okay, its lost strength, okay, and you can regain the strength. Okay, that is how it is done in the industry, right? Having understood spheroidization, now we have another heat treatment process which is called as ash-tempering. Okay, ash-tempering is nothing but you want to get, okay, you have the material and you want to transform the ash, that you want to get the instead of ferrite and cementite, you want to get bainite. Okay, so bainite, you already know, it is again a combination of ferrite and cementite, but ferrite with a lot of dislocations. Okay, as I already mentioned, this ferrite is having hardness more than what you see in the ferrite in perlite. Okay, in bainite, the whatever ferrite you have, that is typically harder, okay, because of large number of dislocations that are induced. How you can get bainite? You see this TTT diagram. If you take a material, okay, in austenitic range and bring it to a temperature at above the nose temperature of the TTT diagram. Okay, if you take, say, I say this is nose temperature because in this C curve, okay, you have the nose here. This is, I call it nose, like, okay, your nose. Okay, if you, this is the nose, all these temperatures, this is temperature, right? All this temperature range is above nose temperature, and all these below nose, these are called below nose temperatures, just for our understanding. Now, if I bring the austenitic range material at austenite temperature suddenly to a temperature above nose temperature and keep it at this temperature for some time, it starts transforming to perlite, completes and gets perlite. Okay, complete perlite you have here, and you know perlite already. Okay, this is isothermal annealing. Okay, in isothermal annealing, if you do annealing at a particular temperature, you get nice fine perlite or coarse perlite, whatever. Okay, depending on what temperature. But if you go below this nose temperature, okay, from here below, and keep it keep your sample at this particular temperature for a while, okay, and after some time you actually end up with bainite. So that process is called ash tempering. Okay, yeah. So I just repeat, if you heat a sample, steel sample to austenitic temperature, that is here, and bring it to above nose temperature, okay, this is nose, anywhere above nose temperature, and keep it at constant temperature, you get perlite, and that is called isothermal annealing. Okay, you know what is annealing. Okay, now if you take the same sample, bring it down below nose temperature, this is nose, okay, below this temperature, and keep it at that temperature for some time, what happens? This is the starting point of bainite. By this time all the austenite is converted to bainite. So now here you have only bainite. So finally you get bainite. And you may ask me why I want to get bainite rather than perlite. So as I mentioned, bainite is having more dislocations present in its ferrite, okay, so that you will get more strength for bainite, okay, compared to the perlite. So bainite is having better hardness and strength. So the particular heat treatment process where you want to get the bainite from austenite is called your ash tempering. Okay, this is a particular TTT diagram for in the case of 1080 steel. Okay, that is one thing. Okay, Now if you see this TTT diagram,